I'm Brian, software engineer working on Spark at Facebook. And this is work done with my colleague, Ergin. The title of the talk is Taking Advantage of a Disaggregated Storage and Compute Architecture. And that phrase is a big mouthful. So I want to define what I mean by disaggregated compute and storage, and then call this Disagg in the rest of the talk. So one way to define this is to kind of compare and contrast to what we call a collocated cluster. So this is our previous generation of hardware, and it may be familiar to many of you, where each node on the cluster serves both storage and compute. So a familiar example is running Spark executors and HDFS data nodes in the same nodes. In contrast to that, a Disagg cluster, we run separate clusters for both storage and compute. So what does a collocated cluster look like? I just want to illustrate a little bit of how Spark works on a collocated cluster. So as you see here, we have a single cluster, and we have many nodes. Just here we only show two, but we have many nodes. And we run Spark, components of Spark in these nodes. And these nodes have all the storage. So each node might have many disks that store the actual data. And the data itself is accessed via a distributed storage, such as HDFS, for reading and writing persistent data. So you can think of this as something like Hive tables, where Spark will read to start a job and then could write output for. But persistent data is not the only data in Spark. Spark actually stores a lot of temporary data, or stores, reads, and then writes, and then deletes a lot of temporary data. And this temporary data is data that is used for things like spilling, for shuffle, and for caching when you cache the disk. So the way Spark uses this is it will read and write from its local file system, and then possibly also get data from different Spark components in different nodes. Now let's see what a Disagg cluster looks like. Here, instead of having a single cluster, we have two separate clusters. The one on the left, the compute cluster, is essentially the nodes are custom made for compute. So you may not have much in terms of storage on these nodes, but you'll have, say, powerful CPUs, maybe lots of RAM. And for the storage cluster, it's the opposite. You may not have much power in terms of CPU and RAM, but you'll have a lot of storage. In this case, we show spinning disks. And the storage cluster runs a distributed file system. At Facebook, we have a distributed file system called warm storage. But you could imagine this also as something like an S3 or like a cloud service, where the storage cluster could be something that you don't actually manage by yourself. But when we talk about Disagg here, I want to make sure that we're talking about persisting the data in this storage cluster and reading it from Spark, which is actually something that many people do today in using things like S3. But the main distinction from that is that we also store the temporary data, the spill, shuffle, and cache data in this distributed file system as well. And so yeah, you can think of that like, since Spark actually uses a lot of temporary data, this actually frees up your compute nodes from having to have high I/O throughputs. So let's take a step back. So why do we even run Disagg at Facebook? We have some benefits. The first is that we improve efficiency. So we're able to, since we have distinct clusters, we can order different kinds of server types that are optimized for the stuff that's running. So again, like compute would likely have like powerful CPUs, maybe lots of RAM. Storage would be kind of the opposite. This also means that we can plan the capacity for these differently. So some workloads can be more CPU intensive, and have less data. And in that case, you can have compute. You could plan for large amounts of compute and relatively less storage, and vice versa. Also, these nodes, because they have different kind of moving parts, such as spinning disks, they have different upgrade cycles as well. And so we can plan upgrades. If we plan upgrades differently, this also improves the efficiency. Another thing is kind of in a management perspective. So since we have these different clusters and essentially different services, different teams can maintain just their service, and they don't have to focus on anything else. Contrast to when we used to run colo clusters, when we had problems, say in our Spark cluster, we would actually have to kind of closely work with the storage teams because the nodes were collocated, so there might be problems with what the storage teams are doing on disk. So it's a much harder kind of problem because you don't have service separation. Now you might be asking, like, why should I be interested in Disagg? So what does Disagg do for you? We can also talk about efficiency for outside of Facebook. For instance, let's assume that you're running in a cloud provider. Here, if you have a Disagg setup, then again you can actually elastically spin up and down your compute and use just as much compute you need at one time, while using a different storage server that is separately built depending on how much data you're storing and how much data you're reading and writing. So we can see parallels to the efficiency argument there. And also in terms of cluster management as well. So let's say you're using S3. We as users don't actually have to manage S3. We just have to know what data is in there. So you would only have to, say, manage your own compute clusters. There's also another benefit that we've also seen at Facebook, but we also see this problem out a lot in the community as well. So when I put into Google no space left on device, actually the kind of the third thing that came up was no space left on device for Spark. And I've heard anecdotally that this is a problem that frustrates people to no end, is that their nodes essentially run out of disk space because of the temporary files. And this is a hard problem because you're capped at the size of your single node's disk if you're in a collocated cluster. While if you're using Disagg, then you're using some storage cluster, and the capacity there combined, of course, is a lot bigger than your single node's disk. And even if all the single node disks that combined would be the same size of your storage service, you still have a lot less chance of actually running out of this whole global storage, as opposed to if you have different, if you run out of a single disk, then your job will start failing. So here's an outline of the rest of the talk. So I just discussed what we mean by Disagg. I want to briefly touch on more on the story about what Spark uses temporary files for. Then I want to discuss how we enable Spark on Disagg at Facebook, then how we deployed it, and then talk more about some more optimizations that we did to run Spark more efficiently on Disagg. So again, this is some background information on how Spark uses temporary files. So the first kind of temporary file I want to discuss is spill files. So spill files get created when you're running a task on an executor, and then your executor runs out of memory. Then you essentially spill that data in memory onto disk as a file. And this could happen many times during the execution of a task. Another kind of temporary file is shuffle files, and these are files that are created whenever you do a shuffle. So the mapper side will create the shuffle file, and then the reader side will read parts of partitions from these shuffle files. And in the case that you actually had multiple spill files on your map task, these actually get merged into the final shuffle file. And then, as I said, when the reducer that's running a reducer task actually goes and reads part of these files. The final class of Spark temporary file is cache files. So Spark allows you to cache data that you might reuse in memory, but also allows you to persist this data. If you're going to be, if you have a lot of data and if you're going to use it many times, you might want to persist this into disk. And so this is another source of Spark temporary files. So now I want to discuss how we enabled using Spark on Disagg. So if you recall, essentially the difference is that we need to store these temporary files in the Disagg storage cluster. So we implemented a new abstraction layer called generic file system. So what this looks like in code is we just take, in Spark core, we take instances of calling Java's file, and then replace it with our generic file interface. And then we implement different implementations for this interface. So you can see here for generic file system, we have our first implementation is actually just the java.io.file system. So we just implement our generic file system using the local file system. Then, since in Facebook we have warm storage, what we want to do is support warm storage as the Disagg file system. We do this actually by making use of warm storage's Hadoop file system layer. So while we haven't done this, it seems pretty straightforward that you can use our Hadoop file system layer to implement in things such as S3 or HDFS or any other kind of distributed file system that actually gives the Hadoop file system type of interface. So given these are the two kind of changes that we make in the Spark core itself, and then given this, when you're running a job, all we have to do is we just have to configure this job to run on a different underlying file system. So this example shows the configuration for when we're running on warm storage. In particular, warm storage has a view that's called temp file system that's used for reading and writing temporary files in warm storage. And then we specify, on the last line, we specify where in this distributed file system we'll be storing our temporary files. So in terms of deployment, we've now gone over a year in terms of using Spark on Disagg. We started off production where where around 20% of our total Spark workload started on Disagg. And then this graph shows kind of how the Disagg part has grown. And our total Spark has also grown, but you can see that Disagg now takes off like a vast majority of all of Spark. So within a year, we kind of got like 15x increase in the workload that we run in Disagg. So I want to talk more on how we actually optimize Spark on Disagg. So we actually have some problems, if you can imagine, going to this different architecture. The first kind of main thing that stands out is that we have a lot of increased latency. So in Colo, we also have discrete rotational and seek delays. We also have that for Disagg, but this problem is actually a little bit exacerbated because of the way that now that we're using a distributed file system, the layout of the files is actually a little bit more random than we had before. But maybe more obviously is that we have these network delays. So we're no longer reading from our local disk, so we have to go through network and pay those delays. Another thing is that, so right now Spark has the assumption of local storage. So in particular, Shuffle service has some inefficient usage of local storage, which I'll go into. So here I want to kind of give you some of the solutions we found for these problems. To go a little bit more on the latency side, so here I have a chart where I show how long it takes to read a 1 GB file, where the x-axis shows that we're reading this file in chunks of these read request sizes. So as you can see on the left side, if you're reading in very small chunks, it takes a lot longer to read this file. And this is actually assuming that we're having random reads. So the overall trend here, where the left side is much higher, is due to the disk seek times. Oh, and these, the orange line shows when you're using our remote file system, and the blue line shows local disk. And then you can see the gap between the remote file system and local disk, especially for small request sizes. And this gap is due to the network delays, because you have to go to the storage cluster instead of just reading locally. So there's actually a relatively simple fix to this, where we essentially just bump up a lot of the buffering. So most of the buffered streams in Spark have a default of 32 kilobytes, and this is clearly not enough when you're doing random reads on a remote file system. So we've bumped up most of these to 1 megabyte buffers, and so we're kind of shifting the curve to the right. Now that actually works well for, if you recall, the spill files and the cached files, because these are kind of bulk read-write patterns. However, for shuffle, shuffle is a little bit more challenging. And here I show a diagram of what we're doing in shuffle. Essentially, each mapper outputs a map output file, and then each reducer actually reads its partition from every mapper. So, for example, if you had 100,000 mappers and 10,000 reducers, this will end up, because every reducer has to read from every mapper, it ends up being, say, m times r number of random reads. Here, it would be up to 1 billion random reads. And given, say, for example, a 50 terabyte shuffle, each partition that gets read is only on average 50 kilobytes. So increasing a buffer size will still not solve this problem, because even if you have a very large buffer, you're only reading 50 kilobytes at a time. So this is actually a very hard problem, which I actually had a talk a few sessions back on this problem itself, where we solve it using a solution called SOS. And this solves it where you're not getting enough disk bandwidth. However, here we at least try to reduce the total amount of latency that we see because of this shuffle read pattern. So what we do is we just read asynchronously. So we open up multiple input streams for each of these for each of the map files, and then we run them asynchronously. So we're only blocking when none of the input streams are returning data. So I want to discuss more on the kind of the shuffle service mismatch that we also had solutions for. So for that, I want to discuss a little bit about external shuffle service and shuffle in general. So shuffle actually under the covers involves reading two files. One is the data file, so the actual map output file that you're interested in the data. The other is called an index file. So for every map output, we have an index file that indexes where in the data file each partition starts and ends. So for shuffle, you first read the index, and then you find out where in the data file you want to read, and then you seek and read from that file. So what external shuffle service does is it allows what's called dynamic resource allocation. So if you don't use external shuffle service, you need to read the shuffle by contacting the Spark executor where the mapper was run, and then reading the data from there. what external shuffle service does is there's an external shuffle service on every node in your cluster. And anything that was written into storage as shuffle, it can serve as basically the file server. So it has two functions. One is that it acts as a cache server. So if you recall these index files, they're pretty small files that will get read by every reducer. So the external shuffle service caches these, and then you don't have to do a disk read for every one of these. The other thing that the external shuffle service does is it acts as a file server for the data. So because when you're doing shuffle, your other executor could be on a different node. It can't read directly from the storage system, so it uses external shuffle service to act as a file server to stream the data over. So this is the view of shuffle service, and under the assumption that you're running in a collocated cluster. Now, if you're actually running in Disagg, one of the inefficiencies here is that you end up actually doing two network transfers. So if your shuffle service is working as the file server, it reads from warm storage, or your or whatever your remote storage system is. And so that's one network transfer of this data file. And then you also have to transfer that to the Spark executor. So what we implemented to optimize this is instead of actually having the external shuffle service read the index file and then stream the data over, it instead actually returns the index value to the Spark executor. And then the Spark executor from there actually goes and directly reads from warm storage. So it no longer acts as a file server, and we implement this by implementing one more type of RPC message where you actually get the path inside your storage system from external shuffle service. Finally, the final optimization I want to talk about is what happens when external shuffle service fails. So in Colo, it actually means that all the local files in that server are no longer available when external shuffle service is unavailable. And this makes sense for Colo because now you have no way of accessing that file. But in Disagg, that's actually a very artificial constraint. So instead, we take advantage of the fact that all of this data is in remote storage. So instead of just not being able to do anything when an external shuffle service is down, instead, if we see that the external shuffle service is not replying, we directly go and read the index file. And then we go read the data file. So we fall back to directly reading the index file. And in terms of practical benefits, one of the practical benefits we see is that when we want to redeploy the shuffle service due to, say, an upgrade, it makes restarting very easy. So previously, you might see lots of shuffle failures and things like this while you're restarting. But with this fallback method, you no longer see those kind of catastrophic failures, even if all your shuffle service is down. But we don't always run this mode because we still want external shuffle service to do the caching in normal situations. So in summary, I discussed how Spark runs on Disagg clusters at Facebook. And so this has been in production for over a year, and now we're running the vast majority of Spark jobs in this Disagg architecture. And I showed how we used a generic file system layer, and so we can use Disagg just based on configuration. And then also kind of the optimizations that we needed to get this layer performant. And in closing, we want to contribute this back to the Apache Spark community. Thank you.
All right, now we have time for some questions.
So you talked a bit about what happens when the external shuffle service fails. But another mode that Spark handles is it's just general fault tolerance. Right? If a node goes down, Spark, rather than using replication like MapReduce would use, it used just lineage and it would regenerate the data. But you don't have that problem anymore because now you're storing, I mean, presumably your warm storage has some replication. And so even if a node goes down, you have some replica available. Did you change the fault tolerance behavior as well to take advantage of that so that on a shuffle fetch failure, or is that just kind of transparent because a fetch failure just never happens in the first place? Does my question make sense?
Right. So I think what you're talking about is actually, so what we do is, so all our shuffle goes through external shuffle service. So when the node is down, the external shuffle service itself is down. And then at that point, we fall back to reading the data directly from a warm storage. So yeah, we should never really see fetch failures unless the replicated, unless we actually have a storage service problem.
Just eliminating fetch failures. Sorry. So you are saying you should be effectively eliminating fetch failures
Yes.
entirely, that you just go to replication automatically.
That's correct.
One quick question. Is the Spark cluster dedicated cluster or for analytical work nodes, or it's a shared cluster with other web services?
So at Facebook, we use dedicated clusters, but I think, yeah, you can use either model, and Disagg actually makes it, easier to do like a shared model because, yeah, you don't need any infrastructure for storing files if you're running in a Disagg setup.
Can you talk about the impact of latency after you moved over to remote storage as opposed to running it locally? I'm
Right.
sure there has to be some sort of performance degradation, but can you quantify that?
So the thing about Disagg and Colo, so we don't have like very apples to apples comparisons because the generation of hardware is different. So we don't really have like any clear-cut numbers, but I guess one of the things I can say is like it's very acceptable. So yeah, I mean, we've done these optimizations, especially the increasing the buffers, because we did see problems with latency. But today it's not like one of our pressing problems.
Have you thought about using the same approach for other applications that may be widely deployed at Facebook, like Kafka or say Elasticsearch? I don't know what other applications may be widely deployed where you want to disaggregate computer storage to scale them separately?
So things outside of Spark.
Yeah.
I actually don't know too well. Yeah.
I'm curious with the Hadoop file system class, why the need for the extra abstraction with the generic file system for talking to java.io instead of just doing like a file colon path through the Hadoop file system class?
So it's because we don't want to completely fork the kind of the code path that we're using. So yeah, we'd like to kind of keep the same code path. So we also run Colo clusters as well. So we have the same code running, and then we can just configure the jobs depending on which cluster they're running. So because of that layer, that kind of becomes cleaner and simpler.
Any plans to open source this? Any plans to open source?
Yes, we'd like to open source
This year?
It's hard to give a timeline, but yes, this year would be great.
So, what's the network bandwidth and latency between compute and storage? Is it? I'm assuming that is it going over the WAN, or it is? It's a dedicated line between compute and storage clusters.
So we use Ethernet, but I don't have the actual like bandwidth numbers and latency off the top of my head. But yeah, for practical purposes, we don't really run into like kind of bandwidth issues at this time.
All right. Are there any remaining questions? All right, let's give our speaker one last round of applause.